You know, if I asked you to draw an atom, chances are you'd sketch a tiny little solar system, right? You'd have a nucleus right in the center and these little electrons just zipping around it like planets. Well, here's the thing. That picture? It's wrong. Today, we're going to dive in and find out what an atom actually looks like. So let's get right to it. What does an atom really look like? I want you to just completely forget those simple drawings you might remember from school, because the reality, oh, it's so much stranger and honestly, way more beautiful. And the key? The one thing that really unlocked this whole mystery for us, the tool that let us finally peer into the atomic world. It's something we see every single day. It's light. Okay, so how exactly does light act as our messenger from the world of the atom? Well, it turns out if we're going to understand the atom, we first have to get a handle on the properties of light itself. You see, what we call light is really just one tiny slice of something much bigger called electromagnetic radiation. Just picture it as this wave of pure energy rippling through space at, the speed of light. But the light our eyes can actually pick up, that's just the very beginning. It's part of this huge, vast spectrum. And when I say huge, I mean huge. We're talking everything from the radio waves bringing music to your car, to the microwaves that give us Wi-Fi, the infrared that we feel as heat. And then you keep going, all the way up to the really high-energy stuff like the ultraviolet rays that give you a sunburn, and even the gamma rays used in medicine. And all the colors we can see, just a tiny, tiny little sliver of that whole shebang. All right, let's jump to our first real attempt at mapping out the atom using this new understanding of light. Back in 1915, a physicist named Niels Bohr came up with a model. And it was brilliant for its time, but as we'll see, it was a flawed first draft. Now, the reason Bohr's model was so powerful, why it caught on, is because it made sense. It felt intuitive. It's the model that gave us that classic planetary picture, right? Electrons on these nice, fixed, circular orbits. You can almost think of them like train tracks circling the nucleus. And his big idea was that electrons could jump from one track to another by either absorbing or spitting out a very specific amount of light. And this was a huge breakthrough. It perfectly explained the unique light signature of the simplest atom, hydrogen. But, and this is a big but, here's the problem. The model was fantastic for hydrogen, but as soon as you tried to apply it to any other element on the periodic table, it just completely fell apart. That neat little planetary picture? Way too simple. The universe, as it turns out, is a whole lot weirder than that. And all that weirdness, it's what led to probably the biggest revolution in modern physics, the quantum mechanical model. Yeah, this is where our picture of the atom gets a serious, and I mean mind-bending update. The quantum model just completely rewrote the rules. We had to throw out the whole idea of certainty, of these fixed orbits, and dive into this fuzzy world of probability. So instead of those neat 2D tracks, we now have these 3D probability clouds called orbitals. And get this, electrons don't just act like tiny little balls. They act like waves, too. It's wild. And this all leads to one of the most fundamental and kind of famous rules of the universe, the Heisenberg uncertainty principle. And what it says is basically this. You can't know exactly where an electron is and exactly where it's going at the very same time. It's impossible. The more you pin down its position, the fuzzier its momentum gets, and the other way around. And that is why we have to let go of certainty and start talking about probabilities. So, okay, if we can't ever pinpoint an electron's exact location, how in the world do we describe it? Well, the best way to think about it is like a mailing address. Scientists use this set of 4 quantum numbers that act like an address to describe the most probable place you'll find an electron and what it's doing. Let's break down that address. The first number, we call it N, is like the city. It basically tells you the main energy level of the electron, so on average, how far away it is from the nucleus. A bigger N just means a bigger city, one that's farther out from the center. Next up, we have the second number, L. If N was the city, L is the street, and this one tells you the shape of that probability cloud, that orbital. And these streets have names you might have even heard before. S orbitals are just simple spheres. P orbitals look kind of like dumbbells, and then the D and F orbitals, well, they get even crazier, looking like clovers and flowers. All right, third on our list is the magnetic quantum number, M sub L. This is the house number on our street. All it does is tell you how that orbital shape is oriented in 3D space. So for that dumbbell shape we talked about, is it pointing up and down? Is it side to side? or is it pointing out towards you? And finally, the fourth number, m sub s. This one describes the occupant living at that address, the electron itself. See, electrons have this weird quantum property called spin. The easiest way to picture it is like a tiny little magnet that can only point in one of two directions. And we keep it simple, we just call them spin up and spin down.
Okay, so we've got the addresses, these orbitals. But how do the electrons decide which address to move into? It's not a free-for-all. It's not random at all. There are very strict rules to this game.
So there are really three main rules you gotta know. First is the Aufbau principle. Basically, electrons are kind of lazy. They always fill the lowest energy spots first. Second, the Pauli exclusion principle says you can only cram a maximum of 2 electrons into any single orbital, and they have to have opposite spins. Think of it this way. No 2 electrons in an atom can have the exact same 4-part address. And third, Hund's rule. This one says that when you have orbitals at the same energy level, electrons will take their own room first before they start pairing up.
And now we get to the big payoff. All this bizarre, counterintuitive quantum theory, you might be asking, why does any of it matter? Well, here's why. Because it perfectly, elegantly explains the single most important chart in all of chemistry, the periodic table.
You know, the shape of the periodic table, it's not random at all. It's not arbitrary. It's a direct map of these electron orbitals we've been talking about. Those first 2 columns, that's the s block, where electrons are filling up s orbitals. That big block on the right, that's the p block. The transition metals in the middle, you guessed it, the d block. The table is literally a cheat sheet for quantum mechanics.
And what's really cool is that this model lets us predict all kinds of trends. Take atomic size, for example. As you move down a column on the table, the atoms get bigger. But why? Well, it's because you're adding whole new energy levels, new cities, to use our analogy, that are farther and farther out from the nucleus. It's exactly what the quantum numbers would predict.
Here's another one. As you go across a row, from left to right, it actually gets harder and harder to remove an electron from an atom. That's because the atoms are gaining more protons in their nucleus, which creates a stronger positive charge that pulls all those electrons in tighter. It makes them much more difficult to just pluck away. And again, this is all perfectly explained by the math of the quantum model. And really, that is the incredible power of this theory. It explains everything. It explains why every single element has its own unique fingerprint of light. It explains how all chemical bonds form. It explains why some things are magnetic and others aren't. It predicts every single pattern we see in the periodic table. It's not an exaggeration to say this is the absolute foundation of all of modern chemistry.
So after all that, we're left with this completely new picture. The atom isn't some tiny, neat little solar system. No, it's a nucleus surrounded by these buzzing, fuzzy clouds of pure probability. It's almost entirely empty space, all of it governed by the strange rules of uncertainty. And that leads to one final, pretty mind-blowing question. If that's what everything is made of, me, you, the chair you're sitting on, then what does that say about this solid world we think we see and touch every single day?